Today we're going to start our new unit called Electrostatics. And based on the name, I bet you can figure that electrostatic has something to do with electrons. And the term static just means not moving. So we're going to talk about stationary electrons. Now when I say stationary, they still will move some, but they don't move as much as, say, if we were studying the flow of electricity in circuits. So it's a little different, okay? So to start this unit, we have to go back to chemistry a little bit and remind ourselves of a few things that we learned in chemistry. And I'm betting you remember a lot of this, okay? So let's first talk about the makeup of an atom. So you probably remember that the atom is made up of a nucleus, which is this part right in here, okay? And then the electron cloud that's around the nucleus. So what we should remember is that the nucleus is made up of the protons and the neutrons, and they're stuck. They're stuck together. The electrons, on the other hand, are a little more free-flowing because they're in a cloud around the nucleus. Now, when I say sometimes they're free-flowing, I do mean sometimes. It depends on the type of atom. In some atoms, such as most metals, you'll have some electrons, and maybe you remember the valence electrons. Okay, so you'll have some of the valence electrons that can move around quite a bit. They're not really attached to their individual atom. But then you'll have other types of atoms where the electrons are very tightly attached. Okay, so we'll talk about those in a little bit. So let's remind ourselves a couple things about electrons and protons. So electrons, we remember, are negatively charged particles. So sometimes I just put a negative sign like this and I put it in a circle. And then protons are positively charged. So usually I'll just go like this with a little plus sign. And neutrons, as their name implies, do not have any charge, right? No charge, zero charge. Okay. And hopefully in chemistry you talked about, because we in chemistry we said that electrons have a -1 charge, and that's just the elementary charge. So in physics, eventually, and we won't necessarily do this in this class, but you will see that there are other ways to measure charge. For instance, coulombs. We won't have to worry about that. We're just going to stick with negative and positive. Okay. We also should have learned that oppositely charged particles attract. I think you probably learned that in chemistry. Okay. And that like charged particles repel. Okay. So an object with excess electrons on it will have an overall negative charge. And an object that is missing electrons will have an overall positive charge. Now you might be wondering, well, what can you have a positive charge if you have extra protons? That's not possible. And that's why we spoke up here about how the protons in the nucleus are stuck together. An atom can't lose a proton. Okay, if it does, it's no longer that type of atom. So remember in chemistry we said, okay, something like hydrogen, for instance, hydrogen just has one proton. Now, if it were to gain a proton, it wouldn't be hydrogen anymore. Same thing with other types of atoms. If you take something that has 16 protons to it, and you take one of those protons away, it's no longer the same type of atom. So we will never have a situation where we're having protons moving around. Only thing that can move are electrons. We can have excess electrons on an object, and like we said, that makes that object negatively charged. And then we can have missing electrons, and that means that we've got a positive charge, but we won't have protons moving around. Now, you're probably pretty familiar with this phenomenon where we have something that's charged, okay? If you've ever taken some clothes out of the dryer, your clothes might have been charged and you've noticed static cling, okay? And that just means that the objects in the dryer have become charged, and we'll see kind of how that works. They become charged, some have become positively charged, some have become negatively charged, and then they're sticking together. Now in chemistry we talk a lot about attracting and repelling. But let's think back. Did anybody ever explain, well, why do they attract? Why do they repel? I'm betting that they didn't. We don't tend to talk about that in our chemistry class. So we're going to talk a little bit about it here, but I'm not going to have a great answer for you, honestly. The reason that positive and negative charges attract each other is because they're exerting a force on each other. So similar to when we see two massive objects exert a force on each other, and we've seen that, right? If you drop a ball, the mass of Earth attracts the ball. It's just a gravitational force. Charged objects will exert what's called an electrostatic force on each other. And if they're like charges, as we said above, they're going to repel. If they're opposite charges, they're going to attract. So what we're going to do today in class, hopefully you'll be there, is we're going to practice charging items. There's 3 different ways we're going to have to charge items, so we're going to practice that. And we're going to see how we can charge things differently depending on if they're a conductor or an insulator. So let's take a minute here and let's talk about what each of those are. Okay, so a conductor is simply a material that allows electrons to flow freely. And we usually say from particle to particle. And some examples of conductors would be metals. Electrons flow very freely in metals. Water. And unfortunately, since we are made up of, or fortunately, depends on your point of view, since we are made up mostly of water, people are pretty good conductors as well. Okay. You might have heard the term, sometimes we say this in chemistry, that metal is simply a nucleus surrounded by a sea of electrons. And those electrons can pretty much go where they need to, or wherever they want to. So most metals make great conductors. An insulator, you can imagine, is pretty much just the opposite. Okay, so an insulator is a material that impedes the free flow of electrons. Now notice I didn't say prohibits, because it doesn't prohibit, okay? But it impedes the free flow of electrons from atom to atom, or particle to particle, or molecule to molecule. Okay. This is because each electron is firmly attached to the nucleus. So some examples of insulators might be something that's made of rubber, so like tires. Okay. Glass is a good insulator. Wood is a good insulator. And air is an insulator as well. Now, having said that, electrons will flow in insulators under certain circumstances. So you might be thinking, well, what would these circumstances be? Well, the most prominent one would be something like lightning. So you can look up on the internet and you can see plenty of instances where lightning has hit a tree and the tree has exploded or ignited on fire, or the tree has fallen down. So lightning will go through a tree, which is just made of wood, right? It's just wood, so it's an insulator. Lightning will go through a tree very easily. So when you build up enough electrical force, you can force electrons to go through even an insulator. It's tougher to do, but it can be done, okay? So the last thing I want to talk about is grounding, because you're going to be grounding some charged objects today, and it's nothing to be afraid of. But we're going to be doing that. So what that means, what grounding means, I didn't give myself much room here. But what grounding means is simply removing excess charge from an object. So once something is charged, sometimes we want to discharge it. And we do that by grounding it, okay? So we basically want to connect the object, connect the charged object to a ground. And a ground can be lots of different things. It could literally be the ground outside, or it can be a large object that can accept extra charges. And we'll say extra electrons, or supply these electrons as well. Okay. So the earth is a good source of ground, okay? People are a decent source of ground depending on the charge. In most houses, we have the actual ground as a ground. So if you look at an outlet in your house, it's 3 prongs. One of them is the hot side, one of them is the neutral side, and one of them is ground. And that ground wire will go through your house, eventually leave your house, and then is tied to a metal stake that is buried in the ground. Okay, and we'll talk more about why we have that ground wire in houses, but just know that that's a great way to discharge extra electrons. Okay, at this point, if you're in class, we're going to go ahead and do the lab, and if not, then take a look at these notes, and we will catch up when you get back. Thank you.